Can you hear me? Okay, good afternoon, and thanks for your patience for staying so long. There is nothing more difficult than stay between the crowd of people you like and their lunch. I'll try not to abuse time, but I would still need about half an hour. Okay, so the second thing I just should say, I am very grateful for invitation of the organizing committee. As you see, the topic which they suggested is a little bit narrower than this fantastic work which you heard this morning. I agreed only because this work is sort of not very well known to the Western community. So I think it makes some sense. And again, about the gratitudes, it would be impracticable to use all people and to thank everybody who have benefited from in the field of superconductor electronics. So I just decided to list very few people who helped me with just to prepare this talk. Okay, so from this morning, you saw that this fantastic discovery of the Josephson effect, and which coincided and accompanied the discovery of flux quantization, and there were the names of London and Divya Fairbank and Dolny Bauer, and Josephson, of course, and Roland Anderson and Shapiro, who experimentally discussed these effects, were prominently mentioned this morning, so I don't need to stay on that. Let me proceed to squids, which also very well discussed here. And again, from theoretical point of view, they are just combination of the flux quantization or incompleted flux quantization in a superconducting loop. And if you put Josephson junction here and just combine the generalized description of the flux quantization, which is with C sine phi, which you have in this junction, you immediately come to this general equation. And of course, you saw this diagram which shows you the flux in the loop and as a function of external flux. And you see that if your inductance is large enough, or critical current, you have this multi-stable or hysteretic dependencies. And from the point of view of computer scientists, computer science or engineers rather, say, oh, that's already memory, right? Because you can remember which state you are. And of course, if you proceed to Diski squid, as was described again in these very nice reviews this morning, you have a periodic dependence of the critical current. So it means that the external current, not even connected galvanically with the squid loop, can control its critical current. So it's essentially a transistor, and computer engineer immediately says, oh, this is logic. I can do whatever logic because this is a controllable three-terminal device. Great. And of course, this was not the first. It was also mentioned that it was not the first attempt to use superconductivity for computing. You can do very nice systems like Buck suggested, and IBM group developed cryotron and memory cells. And this was done, which means first computer experiments were conducted early in the late 50s. And of course, the parameters like time and energy per bit were very inferior to what we have now. But it's interesting to notice generally about physics that it's not exactly related to Josephson effect. It was related to the inability to do lithography better than, or patterning rather than 1 millimeter. If you scale cryotrons to the numbers to say 100 nanometers, which we have now, you arrive about at the same numbers like 1 picosecond and 10 to the minus 19 joule per bit, which we're playing right now. So it's interesting that ability to do digital thing with superconductors, not directly related to Josephson effect. But what Josephson effect really did for computing at that time, in the beginning of the 60s, it allowed you with not very perfect lithography, limit critical currents by order of magnitude, beat them down, and then brought everything to a very interesting domain. Now, hearing about these cryotrons, it was very interesting time everywhere in the Soviet Union, including. Everything was very optimistic, society-wise, science-wise, and of course in the Soviet Union there was a very healthy skepticism about the leadership of the country, about government, but somehow it didn't spread to other things. We were very optimistic about the future of mankind, about the future of science, engineering, electronics. And electronics is very important because at that point, the progress of electronics really resided on scientists who wanted to do more complex calculations, not on teenager girls giggling and sending each other text messages. So it was very different motivation for what we're doing. So it was comparable with very optimistic view of the world and of the society. Okay, so one of these very optimistic groups you see in 1960 at the doors of Kapitsa Institute, famous Kapitsa Institute. They are students graduating from Physico-Technical Institute. And I'm showing that because there is one very special person, Simon Berkovich, who is now in Georgetown and Washington. And he is a genius. He's one of the key geniuses which, you know, Soviet Union was always in the 50s and even in the 30s, was very strong on experimental and theoretical low-temperature physics. But I think it was Berkovich who sort of projected that to electrical engineering. Essentially, using these cryotron things, he invented associative memories much more sophisticated than West played with. Unfortunately, this work remains unpublished. In my paper, which I published, this year is published in Physica C, you can find a citation, you can find a reference to Reminiscence by Simon, and my advice to have a look at that, because this guy is enormous. And so it's interesting, in the Soviet Union at that time, not only low-temperature electronics, superconductivity was very good. Of course, you remember the names of Landau and Lifshitz and Abrikosov and Gorkov and all this crowd, Shalnikov and Sharvin. But also, the computers were very good. The Soviet VT6 was comparable to Western prototypes. Then the society started to rot and all these advantages were squandered. But at that time, and the main institution was ETM-AVT, okay, some acronym. And essentially, Simon Berkovich joined this institute. And if he had a better manager, this would lead to very big advances. Unfortunately, the group was very weak. And Simon struggled there for a few years, and then he moved to what is called in Russian according NIFIP, which is Institute for Physical Problems in Zelenograd, which was Soviet response to the American Silicon Valley. It's a place about 30 kilometers west of Moscow downtown. And there he organized his own group, and in particular he invited another nice guy with the name Gennady Lapir. And this Gennady Lapir was a guy who eventually involved me into the computing. Let me just remind you what was the background at that time in the West. I would pass through that very rapidly, that after the demonstration of switching of a tunnel junction from supercurrent to resistive branch by Yuri Matisu, people realized that you could do everything using Josephson junctions, and immediately this went to essentially logic, and the first version of the gate which you used was called cryotron, just like Bach's cryotron, and Matissou called it tunneling cryotron. So, and you see that it's a copy from his paper. So even you see that even the layout was of Josephson cryotron, or tunneling cryotron, was similar to usual phase transition cryotron. So essentially they moved from one philosophy to another. And as I mentioned, they used squids, of course, to do flux memory. But the basic idea was of so-called latching logic was, of course, switching from superconductor state to resistive state when you either beat down your critical current by this external, by control current, or like Ted Fulton did in Bell Labs, by direct injection of your control current in the cryotron. Essentially, results are the same or close to that. And you, of course, know the story with latching logic. IBM, who organized a big group doing that, suffered from several problems. In particular, Josephson junction technology was on lead alloy, which didn't have too large variability. And second, of course, there was this punch-through effect, which means when you switching from S to R is very fast, switching to R to S is very slow and very complex dynamic process. And though as the year 1938, Bell Labs pioneered, Jim Rowell, Michael Gorovich, pioneered this tri-layer aluminum technology, which we're still using nowadays. It was too late for IBM project. It was closed in 1983. And Japanese continued until early 90s. It demonstrated wonderful devices for that time. This was, what's that? 23,000 Josephson junctions, 1993, under the leadership of Shinya Hauser. But again, because of this punch-through effect, it never made it because CMOS already approached this. Okay, so this was a background of our work. So again, I met Lapierre in 1972, and we started to think how we can work together. And that time, I had a bright young graduate student who just graduated, Vasily Semyonov, and I implanted him to NIFEB group in Zelenograd, and we started to work together. And here, Vasily, very young at the time, is shown with a manager of the whole group, Petr Bakhtin, and there was a separate technology group managed by Vladimir Markov. So they started to work together, and we started to work together. We were not only the only group working in the field. There were a group in St. Petersburg, Kharkov, Novosibirsk. Also in Kiev was a very interesting group. It would work in the Institute of Theoretical Physics doing technology. And the leader of this group, Igor Vaitovich, should be credited a lot for maybe not as much as progress of his technological work, for organizing yearly summer schools in Zhukin, very close to now ill-famous Chernobyl. But it's a wonderful place near Kiev on a nice river in a pine forest. And we discussed many things just sitting on the beach. And the enthusiasm of this crowd and eager how it was done, still unparalleled for me. It was fantastic times. Now, what we did, of course, we didn't want to do what IBM did and Bell Labs. And partly because we understood that it's sort of doomed, and we just proudly wanted to do something else. And our direction of our work was the following. Let's pick up this basic idea that you can control critical current by external current, fine. But no need to use tunnel junctions, because at that time, my background was doing these Josephson junctions and weak links and bridges, etc., mostly from theoretical point of view, a little bit of experiment. So we saw it's possible. And so our main emphasis was, let's sophisticate these cryotrons with Josephson effect, but with non-hysteretic IV curve, which is, so let's do non-hysteretic IV, and I still would be able to control output signal by input signal, which it would be very close to transistor. And bureaucracy was enormous. I could tell you, I would stay 2 hours speaking just how harsh bureaucratic barriers were. What we imagined, even to take several US patents and British patents and everything, we're really proud of our work. Now, the projection to today here, so I still think that, by the way, it's a very interesting side, current injection, everything was very much optimized. It was, I think it's still proud of this work. But, of course, the fab was pathetic. NeFAP was initially created to parallel Silicon Valley. Very fast they realized that they would not do that, so they more and more switched to reverse engineering of the Western chips stolen by KGB just to reproduce them with a few years delay. And of course, this approach doesn't give you good technology. It doesn't give you flexibility. And we never were able to implement these ideas with any degree of reproducibility. By the way, projecting on current work, I see with big pleasure the revival of this idea of doing logic not on tunnel junctions, but on weak links. And recent results, in particular, reported yesterday by NIST, of highly implanted, say, silicon implanted by niobium and other conducting weak links, I think it's very healthy by a simple reason that they require several nanometers interlayer between superconductors, and while usual tunnel barriers are less than 1 nanometer. So it's much more reasonable to expect that you would be able to control thickness better. So I like the revival of this thing. Okay. So the second direction of our work was, of course, this reversible computation. And of course, if you take a squid, again, RF squid, we'll know how the potential profile of this thing look like. If it's hysteretic, it can have several states. In particular, 2 states if your inductance is not too high. So on the top of that, we imagined that you can do, instead of Josephson junction, to put controllable Josephson junction. Maybe a long junction like Matissou used, or just additional DC squid with small inductance. It's trivial. It's used everywhere now. For that time, it was new. Okay, so, and here immediately you can do very interesting things. Of course, applying the flux to your situation, you can just crudely switch your state from this state, you tilt this potential, boom, your system goes here. It's sort of irreversible switching, where you dissipate, say 30 or 100 kBTs energy as a minimum, because this barrier separating the 2 states should be high for these purposes. However, since you can control the critical current as well, which means height of this potential barrier, you can do something smarter. You can take your squid and say you're sitting on the right. You can suppress the barrier first, then gently, slowly roll over your potential to this position, and then to restore the barrier at 0 flux. Hence, you can make a reversible computation. And, okay. By the way, it's interesting that doing that, you can beat not only this pseudo limit of E larger KBT, your energy may be smaller than KBT, the idea which first put forward by Charlie Bennett and IBM, but you can also beat apparent quantum limitation. Your energy may be much smaller than h divided by tau, and we calculated that, and it turned to be true, and we still believe that it's true. And it's interesting that this work is now also may be projected by recent work Vasily Semyonov's team and some other people are trying to implement this demonstrate this reversible computing. I think that Vasily is very close to KBT, but unfortunately this thing is still just transfer of energy, is not computing yet. So we need better effort, but I believe that demonstration of computation with energy per bit less than KBT log 2 would be very important psychologically, and I would encourage this work to continue. So what we did with this parametric Quantron thing, which of course was, we call this parametric Quantron. Okay. So we immediately started to do systems. At that time, we got a very nice new student, Sergei Rylov, or Rylov pronounced in this country, okay. And here, you know, many of you know that he is outstanding. He is at IBM, not doing superconductivity anymore, unfortunately. And he is self-handedly advised by Vasily Semyonov, derived a very complex system on 7 layers of complexity without using essentially any computer-aided design by hand. From the interferometer junctions all the way to system which eventually had like 10 to 7 devices. There was outstanding work, and it gave very interesting results. What the results were? Using this parametric Quantron idea, reversible computing, you can really carry it through the system. You can have almost negligible, almost zero computation. That's positive news. Bad news is that, first of all, you should go it slow, and it was clear from the very beginning. Though slow in superconductor electronics is a few gigahertz slow. On the other hand, the worst news were that when you do practically all these gates, you see that this operation is extremely sensitive to variability of your things, so coupling between Swede loops, critical currents. At that time, it was completely impracticable. But now, maybe we should come back to this idea. By the way, it was an interesting, just for a few seconds of non-superconductivity, there was an interesting continuation of this idea. In 1996, Sasha Korotkov and I realized that you can carry over this idea to single electron tunneling, and you could do what we call single electron parametron. And equally, like our parametric Quantron was later reinvented by the Japanese, like quantum flux parametron, this idea was also not reinvented, worse than reinvented, because these guys were familiar with that as quantum or quantum dot Celler automata in the worst version, and was promoted very much, without acknowledging the fact that to implement this technology, you need, again, a few % accuracy of everything. And because of that reason, it didn't give any good results in any implementation. But I still think that this time may come, because the problems with energy consumption in semiconductor electronics, in data centers, et cetera, you know how bad they are. It's about 10% of the power consumption in this country, so it becomes a big issue. Okay, so again, we were very frustrated that we needed to provide few % variability, which was completely out of our experimental reach because of few fabrication. So we flipped back to irreversible stuff and started to think about the idea of using SFQ pulses. It was, of course, clear from work we were standing, of course, on the shoulder of the giants, like Hurrell and Silver, who understood very clearly, and it's just simple induction law, but everything simple should be invented, that if you change the RF squid state of hysteresis, this pointer really doesn't obey me. Okay, the state of this loop, in the moment when you switch between flux state, by Faraday induction law, you should have a pulse with area, integral VDT, of even to 1 phi naught. And 1 phi naught is about 2 millivolts by picosecond. And these pulses that short, as calculation by Dick Kautz and experiments at IBM showed, they may propagate by, say, all intra-chip distances, like 1 centimeter, with very small distortion and attenuation. This was one motivation of this work. And the second motivation was, of course, nice work in the University of Tohoku by the team of Nakajima and Onodera, who developed all this wonderful logic system using flux quanta propagating in Joseon transmission lines. The only bad aspect here that was that there was a completely impracticable, which it would take a sort of 1 centimeter for one logic cell, and timing would never be settled because they assumed that all these fluxons propagate with the same velocity and arrive at that time to the point where they're both needed. So this was a problem. And the third influence, of course, what really pushed us over is that, of course, Curiel and Silver calculation that you can do static frequency divider, and especially the demonstration by Clark Hamilton of this fact. Just a second. Okay. Because these pulses are like 2 millivolts, and we were always in the doubt, okay, you have it on paper, but you know, I am a theorist, so I never believe any theory. So 2 millivolt pulse, maybe it's too small to switch something. We need the experiment. And essentially, Clark's experiment gave us this assurance that it can be done. And I'm very happy that IEEE Council of Superconductivity acknowledged his great contribution to this issue. Now, okay, so encouraged by that, we suggested this RFQ system, and the general idea, of course, is that you have a set of quantizing loops, and when I switch one, it generates this SFQ pulse, and this pulse can go somewhere else and switch something else. Of course, this is a very general sort of two general scheme, and okay, here. And of course, this should be really cast some tough solutions. And I think the key point was invention by Oleg Mukhanov and Vasily Semyonov of an effective NOR cell. Because yes, on triggers, they are trivial, you just propagate your quant. But how do you do NOR? And the idea was, first of all, to stop calculation, to stop SFQs at each pulse. So from the point of view of computation, it's not a combination logic, it's a finite state machine, which means when your pulse arrives somewhere, it stops and waits for the clock signal. Now, it's, as soon as we sort of accepted this idea, then everything, I would really prefer a pointer. Okay. And essentially, this is a NOT cell. So you have a quantizing cells with two junctions. And if in its original state, if the clock pulse arrives, it switches this junction, throwing out your flux from here. And there is nothing propagated to the output. However, if, if your clock arrives and nothing happens, it switches this junction, and the pulse propagates to the output. However, if you had at the previous clock cycle, you had SFQ pulses arriving here, it switches the flux state of this loop, and then the clock pulse throws up this thing out of the entrance. So you have delayed NOR function. And this was the key, and it was very practical. Okay. So we, of course, needed an experiment. And it was, again, technology was always his issue. but there was a small group headed by Valery Koshelets, informally headed by Koshelets, in Institute of Radio Engineering and Electronics. It's like 300 meters from Kremlin. Very interesting location, very downtown. This is where Lebedev discovered pressure of light in 1912. And they did, Vasily and I think Sergei also helped, and Oleg designed this circuit, and it was fantastic by these standards. First of all, it had to be self-tested because there was no equipment to do gigahertz, especially at these small frequencies. Second, it should be extremely simple fabrication because fab was a 10 microns minimum feature set. Third, it should be not more to 2 levels of superconductor because otherwise it would be doomed. And it was designed, and the design was very smart because look at this design. If you look, okay, cursor is out of my control. Look at the bottom right of the slide. It was, if it were just simple frequency divider like we're using now, it would produce output voltage half of the input voltage. People would not believe us. It would say, okay, your DC voltage is divided somewhere. So the system was first to divide the strain of incoming, generate train of incoming pulses, divided by 2, and added to the initial. So the output DC voltage, which was measured, would be 3 seconds of the input voltage, and try to organize it without the idea of computing. Okay, so it was done, and the maximum frequency was 30 gigahertz. And at that time, it was a world record. And this was sort of resonated through several layers. Okay, how much time do I have, Horst? 5 minutes, okay. At the same time, of course, these were very turbulent times. If you, 87, several things were happening. First of all, in the same lab, in our lab, Singer Electronics was born at the same time, and probably many of you know the story, so it certainly interfered with our activity here. Second, High-TC arrived, and as you know, Soviet Union has the same physics Woodstock, different version. So all this fast. And of course, I was, and we were as enthusiastic as everybody about High-TCs. And I think I observed in early March, was first to observe at night Josephson effect in the second Soviet example of IBCO ceramics. And Leonid Kuzmin and I, for 24 hours, the same April, honestly believed that we discovered room temperature superconductivity, right? And it was really nerve-wracking. Okay, nevertheless, by summer 1987, the flurry of new results settled a little bit. So we knew coherence distance, more or less. We knew penetration length of the High-TC materials. And Sasha Zorin, who is now in PTB at Braunschweig, Vasily Semenov, who is around here, I think, and myself sat down and calm, tried to take our breath, and estimated how much High-TC may give to electronics, to superconductor electronics. And the answer was nothing. And you, by now, you of course now know the arguments, which are in that right corner, that in order to withstand high temperature operation, you need to boost IC. In order to need IC, you need to reduce L. You need to reduce L. You need your penetration there scaled, BCS scaling of, and High-TC's material, EBQO, and nothing which appeared since then have the scaling of penetration. So which means the answer is that if you want room temperature superconductor electronics, please come back with a superconductor with 1 nanometer penetration depth. Then we are ready to speak, but not before that. Okay. And we, of course, published this paper in Russian, and what we earned was a deep hostility of all Soviet superconductivity establishment. And when we eventually published in English, it was not hostile, but it just swept under the rug. And people continued to waste enormous money and time, attention on high-TC superconductor digital electronics for 10 more years before it finally collapsed. And it was quite an experiment. Okay, anyway, my last transparency I would spend. I don't have time for very interesting story how with our Politburo ordeal when Mr. Gorbachev shook my hand and whatever. I don't want, and it's essentially was a result of a illiteracy of a Pravda correspondent who mistook NEC results for memory cells for a factor of 220 squared because of confusing multiplication with division. Okay, so as a result, we got this big project called Contact, and I had $5 million a year for our team, which was quite sizable at that time. And this happiness lasted for a little bit more than a year. We bought quite a few equipment, which is still used in Moscow State, but in 1990, Soviet Union went belly up. All our funding was, of course, canceled. And from this point, there was, again, was big disappointment. I had nothing, didn't want, and I had my personal complaints about the Soviet system by that time. So I decided to go out, and there was a trip to the United States in summer 1990 where I did an invited talk about RSFQ at ASC meeting in Snowmass, Colorado. And it was the first time when I think Western community understood what we were speaking about for 5 years. Okay, and then gradually the core of our group moved to the United States. Superconductor people mostly to Stony Brook and Cypress. And here, as you probably know, this is a more known part of the story. Within 2 or 3 years, we essentially did RSFQ, the dominating digital superconductor electronics technology. Okay, but it's another story. Have a nice lunch. Thank you.
Nice. Thank you, Kostya. Is there one question for Kostya? Okay, then I guess I join. Enjoy your lunch. Oh, one question, Sam.
Good question, thank you. Sam, I think that superconductor, digital, electronic, low temperature, of course, until we invented something new, materials. It would never beat CMOS, right? Because CMOS has too big customer base, handsets, whatever, which we would never have, right? But it may be a self-supported field. I would not say niche, maybe by sort of $300 billion, it may be a niche, but it may be a few $billion, very comfortable niche in high-performance, low-power computing. However, for that, there's not enough technical advances. In computation, superconductor digital electronics still have not won, because even in high-performance computing, many operations may be paralyzed, in particular, image processing and movie processing. However, there's a community, or rather several communities, which do need low latency. Not as much speed as low latency, and where you cannot parallelize your stuff between distant processors. These communities exist, they need computing power, and I think the role of this community should be organize that communities into customer support base. And here, of course, it's easier to criticize. Every fool criticizes, and I do. But I don't see this motion in the superconductor electronics community to organize these groups. At least I don't know of any. And until this happens, we would live on government subsidies, which is the last thing I would like to be.
Thank you very much, Kostya. Let's thank Kostya one more time.